Now we will see this question. A 6-pole 3-phase alternator running at 1000 rpm supplies to an 8-pole 3-phase induction motor. So there is a 6-pole 3-phase alternator. Okay, now its speed is 1000 rpm. It is a synchronous generator. Its rotor is running at 1000 rpm. Supplies to an 8-pole 3-phase induction motor. Now it supplies to 8-pole 3-phase induction motor. Now the rotor current of induction motor has a frequency of 2 Hz. Now the speed at which the induction motor is running, he is asking. Students, now the induction motor, the stator of the induction motor holds the 3-phase winding. To this 3-phase winding we need to give the supply, then only the induction motor will run. From where that supply is coming? That supply is coming from this synchronous generator. That supply is coming from synchronous generator. Now let us concentrate on synchronous generator first. It is a 6-pole machine and the rotor of the synchronous generator is running at 1000 rpm, students. That means this is the synchronous speed of the synchronous generator. So from the formula Ns is equal to 120 F by P. Okay, if the rotor of the synchronous generator is running at a speed of 1000 rpm, where synchronous generator has 6 poles, what is the frequency of the supply that is generated by the synchronous generator? Okay, therefore what is the frequency of the supply given by the synchronous generator? Therefore what is the answer here? F equal to 50 Hz. F equal to 50 Hz. That means induction motor stator has 3-phase armature winding. So in that armature winding, the currents and voltages will have the frequency of 50 Hz. Will have the frequency of 50 Hz. Fine. Now 50 Hz, right? Yes. So what is induction motor? Okay, it is a singly excited machine. We need to give supply only to the stator winding. Hence I have given supply to the stator winding. Now the rotor is rotating. Now the rotor rotates at a speed other than the synchronous speed, or we can say rotor rotates at a speed very close to synchronous speed but less than the synchronous speed. Okay, now see here, there is one data given. The rotor currents has a frequency of 2 Hz. We know that the rotor currents or the rotor voltages has a frequency of slip frequency. Okay, so this is equal to 2 Hz. Now what is F here? This F is the frequency of the currents and voltages of the stator. Now this S into 50 is equal to 2. Therefore S is equal to 1 by 25. Okay, so this is the slip value. Now students, see here, when I have given 50 Hz supply to the stator of the induction motor, so what is the generally, if we talk generally, after giving power supply to the stator of the induction motor, now the currents has a frequency of 50 Hz. A 3-phased balanced currents will flow in the 3-phased balanced winding of the induction motor. Then what will happen, students? Then the rotating magnetic field is generated. Now this rotating magnetic field rotates at a speed of synchronous speed. Then what is the synchronous speed of the rotating magnetic field, students, here? The synchronous speed of the rotating magnetic field is 120 F by P, where P is the number of poles of the induction machine. Now therefore this is 120 into F. F is the frequency of the currents and voltages flowing in the stator, which is 50 divided by, so how many poles of induction motor? It is 8. As simple as that. So this is the synchronous speed. This is the speed at which the rotating magnetic field inside the induction motor is rotating. Fine. Now what is the relation between the speed of the induction motor and this synchronous speed? N equal to Ns into 1 minus S, students. As simple as that. Therefore N is equal to 120 into 50 divided by 8 into 1 minus, what is the value of S here? 1 by 25. We can easily find the speed of the induction motor. So let us calculate this value. So it will be 24 by 25. Okay. So let me write down here. So this is 120 into 50 into, so this is 24 divided by 25. 25 into 8 is 200, students. So 54s are, 46s are. So therefore, which is 720 rpm. So this is the speed at which the rotor of the induction motor is rotating, students. Now what is the synchronous speed? What is the speed of the rotating magnetic field here? How much? 4 2s are, 4 30s are. Okay, 15s. So it is 750 rpm. Okay, so 750 rpm is the speed of the rotating magnetic field. Obviously the speed of the rotor is close to that 750 rpm, but has to be less than the 750 rpm. And what is the only option here? It is nothing but 720 rpm, right? So this is one very beautiful question. Okay, now the results of this slip test. So we have done the slip test, right? What is a slip test? It is a test, it is an experiment to be performed on a salient pole mission to find the direct axis synchronous reactance and quadrature axis synchronous reactance, XT and XQ. Right. Now we have conducted the experiment and we have found the values of XD and XQ by taking the readings of the voltmeter and ammeter, if you remember that. Okay. So that means there is a voltmeter in the test, there is an ammeter in the test. Voltmeter have, we can take different readings, and ammeter also it will give different readings. So voltmeter have maximum value and it will have minimum value, and the ammeter also has maximum value and it will give the minimum value. Okay, now what I told you in that experiment, in that slip test, okay, after observing the values of the voltmeter and ammeter readings, XD is equal to maximum reading of the voltmeter by minimum reading of the ammeter, students. Yes, right. Similarly, XQ equal to minimum reading of the voltmeter divided by maximum reading of the ammeter, students. Yes. See, one thing is very sure. What is that? XD is greater than XQ. XD is greater than XQ. Just observe here. Okay, so I think option B cannot be true. So definitely, because XD is less than XQ. Similarly, definitely not D, because we know this point. XD is greater than XQ. Now observe the two options. A and C is only remaining here. So we already got V max, V minimum, A max and A minimum. So what is Vmax? 180 volts, 108 volts. What is I minimum? 10 ampere. Therefore, what should be the value of XD, students? XD equal to 108 volts by 10 ampere, which is 10.8. So we got the answer. And what is XQ? XQ is equal to minimum reading of the voltmeter divided by maximum reading of the ammeter. Where is the minimum reading of the voltmeter? 96 divided by maximum reading of the ammeter, 12. So which is 8 ohms, right? So this is XQ and that is XD. A very good question. Okay, so you can get these type of questions particularly in engineering services exam, state public service commission exams, SSC junior engineer exams, and yeah, they may be asked for 1 mark in gate exam as well. A 3-phase 50 MVA 10 kV generator has a reactance of 0.2 ohms per phase. Fine. The reactance of the generator is given. Hence, the per unit value of the reactance on a base of 10 10 MVA and 25 kV. Students, we know the formula. What is the formula? Okay, so Z per unit or X per unit is equal to actual value, students, actual value. So for your clarity, I will write in ohms into MVA divided by kV whole square, kilovolt whole square. Students, this MVA and kV has to be base values. Okay, so therefore what is the per unit value of 0.2 ohms per phase? So that is equal to 0.2 into, so what is the MVA base value here? 100. You have to put only 100, not 100 into 10 power 6. If you put 100 into 10 power 6, in kilovolt base also you have to put 25 into 10 power 3. Then it becomes 25 whole square into 10 power 3 whole square. Therefore 10 power 6 got cancelled. Don't get confused there. What I am saying here is, so it has to be 100 and this has to be 25 whole square. If you put 100 into 10 power 6, you have to put here 25 into 10 power 3. 10 power 3 whole square, 10 power 6 got cancelled. Now calculate this value, how much this is. So therefore it is 1 by 5 into 25 into 25. So this is 4 times. Fine. So I will take like this, 400 divided by 5 into 25 into 1 by 100, just to make the calculation very easy. So this, therefore this is 16 times and 3.2. So 3.2 divided by 100, which is 0.032. Right. So that is the answer. It's just a matter of calculation. 0.032. The short circuit ratio of a 3-phase alternator should be high. Yes, it should be high because there are many advantages. That's why it has to be high. Right. A is correct. A high value of short circuit ratio will decrease the value of voltage regulation. I told you. Okay, because short circuit ratio is, in fact, I can write is equal to 1 by XS saturated per unit, right? Yes. Now voltage regulation is directly proportional to IA into ZS or XS. That means short circuit ratio is inversely proportional to voltage regulation. Okay, so my voltage regulation has to be low. That means it is a good voltage regulation. For voltage regulation has to be low, the short circuit ratio has to be high. Right. So a high value of short circuit ratio will decrease the value of voltage regulation. That means it is a better voltage regulation and increase the maximum power output. Okay, isn't it? Because what is the power output? EF into V divided by XS sin delta. Right. Okay. Now see here, short circuit ratio is inversely proportional to XS. Okay, so power also inversely proportional to XS. If I increase the short circuit ratio, this will increase the power. Yes, in fact, what is the maximum power? This is the maximum power. If I increase the short circuit ratio, my maximum power will also get increased. Okay, therefore both A and R are true and R is the correct explanation of A. Right. And of course, by increasing the short circuit ratio, you are also increasing the stability of the machine. Right. Which of the following is the primary reason for placing the field on the rotor in alternator? So in alternator, okay, the field is placed on the rotor. If you see the DC machine, the field is placed on the stator where the armature winding is on the rotor. Now see students, what is the reason for this? What is the reason for this? Because what is an alternator? This is the synchronous generator. It is supplying power. Where you are getting power? You are getting power from the power plant. So in the power plant, okay, somehow we will able to run the turbine, and that turbine is connected to the rotor of my synchronous generator. Therefore, my rotor of the synchronous generator will rotate and that generator will generate voltage. All this power is coming from that synchronous generator. So huge and high amounts of voltages and currents it has to deal. My synchronous generator, from where we are getting from the stator of the synchronous generator, isn't it? Yes, from the stator of the synchronous generator we are getting the voltage and current. So obviously if there is that much amount of voltage, see, if there is a load when there is a load there is a current. If there is no load there is only voltage, right? Yes. So if there is that much amount of voltage is there, I need to provide insulation. Okay, if the winding which is dealing with the high amount of voltages is stationary, then providing insulation will be easy work, right? Therefore, what should be the answer here? Insulation of high voltage is made easy on the stator than on the rotor, because stator is stationary. It is easy. Which of the following methods gives more accurate result for determination of voltage regulation? It is American Standards Association method or American Institution Standard method. So this is the one which gives more accurate result for the voltage regulation of an alternator. Next, how can the reactive power delivered by the synchronous generator can be controlled? Now tell me, how can we control the reactive power delivered by the synchronous generator, students? Delivered by the synchronous generator can be controlled by changing the prime mover input, by changing the excitation, by changing the direction of the rotation, by changing the prime mover speed. So if it is an alternator, by changing the prime mover speed, you can only change the frequency of the power supply it is generating. By changing the direction of the rotation, you can change phase sequence. You can only change phase sequence. If it is RYB, you can do it for RBY. You can change the phase sequence. By changing the prime mover speed, you can only change frequency of the supply or frequency of the voltages the generator is generating. By changing the excitation, students, so by changing the excitation, we can able to change the reactive power. Therefore, we can able to control the power factor of the generator or the motor. Therefore, we can able to control the power factor of the synchronous machine by changing the excitation. Right.